Hi, my name is Thomas Weible. I'm co-founder from Flexoptix, a company which is specialized in optical pluggable modules. And this presentation I brought this time to SwiNOG is more a future prospect, what will happen in the next couple of years when it comes to technology of 400 gigabit. About myself, I formerly was involved within Flexoptix doing mainly the software development. Some of you might know the product we develop, the Flexbox. I moved more and more towards now to the technology itself, to the transceiver technology. And yeah, that's the talk today about it. Don't get confused with this transceiver generation. There is even a better title for that presentation. It's called From Cyclops to Triclops. It's not made by me. I got this hint from Aaron Hughes from 6Connect. He met me on Weible and said, "Hey, Thomas, you should rename your presentation like that," because I do have one section in there which is a theory part, and there you will see the Triclops and also the Cyclops. And the second part is more a practical hands-on one. So let's start with the theory, and it's quite straightforward. I assume every one of you are familiar with a rectangle shape of a signal. So we got that represents one bit in a perfect world, and this bit has two events. Basically, the high event on the up there. There is a can do it like this. We got a high event up there, and we got a low event down there. That's pretty straightforward. And this applies mainly to the technology which we have currently up to 100 gigabit. Two events, high and low. Now, some of you might have heard a term of an eye diagram. And when I talk to network engineers, people say, yeah, we need eye diagrams and we need beautiful eyes. That's something really important. Open, wide, beautiful eyes. But what is so important about an eye diagram? And that's what I want to show now. First of all, when we have our signal, and here we have a sequence of 3 bits in a row, so 0, 1, 0, these 3 bits go through 3 events basically. So we start from low, going up to high, and down to low. And that's not only in a sequence of 3 bits, and we have 2 events, so 2 to the power of 3 gives us the math 8. We have 8 different states, or which these three bits can have. So starting from the top again, 0, 1, 0, going down to 0, 1, 1, or 1, 1, 0, or even 1, 1, 1. Now, when you overlay that, you will get something like that down there, and that's basically the basic foundation of an eye diagram. Up there, you see a real eye diagram, which is measured from a 100 gigabit transceiver. And so you see here the high-speed signal going through those different areas where it's measured. And you might wonder why it looks so weird and it looks more like a sinus shape and not a rectangle any longer. We are talking about high-speed signals and in a frequency of 25 gigahertz, and the rectangle doesn't exist any longer, so it's more that sinus then later on, just due to the fact of that high speed. And so we have 2 events, high and low, representing one single bit. What does make an eye diagram is basically that shape in the middle, and that's a really important one. So that's what gives us that possibility that our transmitter goes through those different states, but it should avoid going through that area, because on the other side of a transmitter there is a receiver, and that receiver needs to detect either it's a low or high event. And if, for example, if our signal would be corrupted, it would go through that area, the receiver wouldn't be capable to identify, hey, was this a high or low event? And that's really an important thing of an eye diagram. So you need that shape, and you need to make clear that the transmitter is able to transmit properly on a high or low level. And that's an important part of an eye diagram, and that's what you want to avoid. You want to avoid dodgy eyes or broken eyes. This was me trying to play ice hockey. I wasn't very successful. But yeah, this can also be a broken eye. Now, as I introduced at the beginning, we are talking about 400 gigabit, and what you have seen so far on the theory part is this more technology from 100 gigabit. Now, for 400 gigabit, it looks a little bit different, and we still take our rectangle shape here now, but what we did, we added 2 additional intermediate steps. And some of you might be familiar with that technology. It's a modulation method. And so the great thing now about this modulation is, so we got now, instead of 2 events, sorry, the high and low, we got now 4 events. So we got low, high 1, high 2, and high 3. And the great thing is, we can represent now 2 bits just with a single pulse instead of 1 bit. And with that fact, we just basically doubled the amount of data we can transmit on the same frequency. And that's one key component for 400 gigabit. The other one I will show later on, that we get actually to 400 gigabit. So how does this monster or this Triclops looks like now? So the eye diagram looks a little bit different. So we got now, instead of 1 eye shape, we got 3 eye shapes in there. And this modulation scheme is called pulse amplitude modulation, or basically 4-level pulse amplitude modulation, and the acronym is PAM4. As you can see, so we have those 4 events here, and we can represent 2 bits, basically having either the symbol 00, 01, or 10 and 11. And as I said already, on the same frequency, we just doubled the data rate now, coming from 100 gigabit up to, I would say, 200 gigabit, and but more later on the hands-on part. Coming to the hands-on, this technology now needs somehow to build up in a transceiver. And before I straight jump onto those 400 gigabit transceivers, I would like to do a recap on the 100 gigabit, which is now mature technology, which is around in the field for a long time. And opening up a 100 gigabit transceiver, we have mainly 2 components in there. We got an electrical side where our PCB is placed. We got here the connector connecting to our host. And this is driven by 4 lanes, 4 times 25 gigabit. Just remember, it's just that single pulse with an on-off keying modulation scheme running at a speed of 25 gigahertz. So these 4 times 25 gigabit gives us 100 gigabit. Simple math. And so those 4 lanes are connected to an optical engine, which is also driven by 4 lasers running at a speed of 25 gigahertz, and also 4 receivers. So that's what we have already in place for 100 gigabit. Now for the upcoming 400 gigabit, there will be 2 generations. The first one will look a little bit different, and here you can see where the double, the second double is coming from, is we increased basically the amount of lanes. So from our host, again, we get 8 lanes now running at 50 gigabit. So on the frequency side, we're still at 25 gigahertz, but we got PAM4 modulation there. We have a double amount of the symbol rate, so instead of 1 bit per symbol, we got 2 bits. We get the 50 gigabit here, so 8 times 50 gigabit gives us 400 gigabit. These 8 lanes are connected straight to to an optical engine with 8 transmitters and 8 receivers. So that's going to be the first generation for the 400 gigabit one. But as I already said, there will be a second generation. That's, in my opinion, the most interesting one. It looks like this one. So the electrical part stays at 8 times 50 gigabit, but we add now a gearbox as it's a tiny ASIC, it's a chip, which takes those 8 lanes, combines it to 4 times 100 gigabit, still PAM4 as modulation, but with the nice benefit, we only need 4 lasers and 4 receivers now on the optical engine, running at a speed of 100 gigabit. And you might ask yourself, hey, why is it so complicated? Why do you just don't reduce also the electrical side down to 4 times 100 gigabit? And the reason is quite simple, it's costs. Technically and theoretically, it would be possible to shrink it down to 4 lanes running at a speed of 100 gigabit, but for that you have to increase the frequency, and that the PCB material which is needed for that high frequency is just freaking expensive, or the longer the traces are, the more expensive it gets. So you can't stick to the current PCB material any longer. You need something like Teflon or ceramic for the PCB material. So it's way cheaper just build a silicon, a chip, place it on the PCB, have the traces shorter, and do the high frequency stuff in the chip itself. From the application point of view, or from the form factor point of view, how will it look like? So you might be familiar with the current 100 gigabit solution, the QSFP-28, and that's the one which shown up there. It has one connector road connecting to our superfast switch, and yeah, that's the current generations for the 100 gigabit transceivers. Now, for the 400 gigabit one, there's the QSFP-DD introduced, and the great thing about the QSFP-DD, first of all, the DD stands for double density, basically, and the great thing about the QSFP-DD is that the slot itself of a QSFP-DD is backwards compatible to a QSFP-28, and that's pretty cool. So you can plug in a QSFP-28 running 100 gigabit, you can plug it into a 400 gigabit slot of your switch. How is this made? Is basically the physics are almost the same. You see that the QSFP-DD is slightly longer than compared to QSFP-28 is having 70 millimeters, and we get here 75 millimeters, so we add a portion of 5 millimeters at the end. And the QSFP-DD has two connecting rows, and how is this backward compatibly made? So when you plug in the QSFP-28 with one connector row into your QSFP-DD socket, only the first row is connecting and not the second one. And that's how the 100 gigabit is made into that 400 gigabit slot. Now for the QSFP-DD, for sure, both connectors need to be connected to your host to run the 400 gigabit there. A second form factor which is introduced now with the 400 gigabit is called the OSFP, and as you can see, the dimensions is a little bit bigger, so it's not the absolute value, these are relative to each other. So the OSFP is slightly bigger compared to QSFP-DD, it's longer and a little bit higher, but the interesting part, and that's where we come later on when it comes to the power consumption, is that the OSFP will have a integrated heatsink. Some of you might remember back those days of 10 gigabit running Xenpack and X2, they also had an integrated heatsink, and this helps to get rid of the heat basically and pump in more power into this kind of transceiver. Why do I mention the portion out there and the dimension? That's a thing what I figured out in the practical field, building networks together with our customers when we introduced the first 10 gigabit DWDM SFP pluses. Some of you might remember 6-7 years ago, those first 10 gigabit DWDM SFP pluses, they had a long heatsink at the front portion, and some of you might ended up with having an issue plugging in that transceiver in a switcher router, plugging into a cable into that transceiver and figuring out, oh, I can't close my door any longer because that portion which sticks out of the first rack unit is too long. Because no one took in consideration that a transceiver can stick out a couple more than 20 or 30 millimeters. And the bad news are for 400 gigabit transceivers, it's defined as well that they can stick out up to 35 millimeters beginning from your first rack unit. And I want to mention that because you have those 35 millimeters, you need another 50 millimeters for your plug, and then you should give that fiber also a little bit bend radius because you don't want to break it or knick it. It's optical fiber, so it needs a little bit bend radius. So you might end up with spacing from the first rack unit to your front door with at least 130 up to 150 millimeters, and that's quite important because thinking of the one-use switches which are out in the market, and I'm pretty sure they will also be in the future like that. They even get really deep from their chassis. So even a 1,000 millimeter rack won't be enough any longer. So you might end up looking for a 1,200 millimeter rack, just getting all the wiring done. And therefore I want to mention that. So even for the 400 gigabit, the portion which sticks out of the first rack unit is going to be quite a decent size. So what kind of applications can we build there? For sure, we can do at the front part here. So for sure we can do straight 400 gigabit. So we got two switches running on a link speed of 400 gigabit from A to B, or from east to west, or how you want to define it. But interesting is also that breakout mode, when the second generation of the 400 gigabit transceivers will be introduced. So having 4 times 100 gigabit, and that also means we have 4 times 4 different lambdas when we talk about a single mode, for example. So we have this 100 gigabit, we can break it out, and that's pretty unique. So we have here a 400 gigabit switch, and we can break it out in 4 dedicated 100 gigabit links. And it doesn't matter if it's going to be QSFP-DD or OSFP, the form factor is equal there. But they both going to support that mode, so having 4 times 100 gigabit on a single lambda. This implies for the QSFP-28 there will be new QSFP-28s coming out on the market running 100 gigabit on one single lambda. That's pretty nice. And when we shrink down the form factors, there also will be introduced new form factors, the µQSFP and also an SFP-DD again for double density. In terms of when we come to the application point of view, thinking about IEEE standardization, LR4, I want to do a small recap what we have seen on the roadmap on 100 gigabit. So this, what I show here, is mainly what the IEEE defined for 100 gigabit on single mode. And here you can see there was no definition for those acronyms which we know, the parallel single mode. So you might know this 4 times 25 gigabit breakout mode, which you already operate in your network. The same applies to CWDM4 or CLR4. They are on the market available, but the IEEE never defined them as a standard. The only thing what they defined there is the LR4, and even beyond that, the ER4 or ER4 Lite. And so the LR4 defined by the IEEE for 100 gigabit has a spacing of 5 nanometer for each single wave, so 4 waves in there having a spacing of 5 nanometers which to each other, so it's called the LAN WDM, and we do this up to a distance of 10 kilometers. Now these lessons were learned for 400 gigabit, because when you look now on the roadmap for 400 gigabit, the IEEE said, hey, we have to make a definition there, because otherwise if we, for example, operate a network where we only control one end and we want to talk to a counterpart, and if there is no clear definition like LR4, people do not know how they can interconnect. Just when we have seen questions in the 100 gigabit world, hey, can we interconnect the CWDM4 transceiver with a CLR4 transceiver? From the optical specs it should do, but is it technically possible? And so these lessons were learned from the IEEE, and also with that 100 gig lambda MSA working group, they said, okay, we have to define not only the long run 10 kilometers LR4, we also have to define FR4, which is basically the old CWDM4 running up to 2 kilometers of distance. So the spacing from each laser to each other is a little bit wider than on the LAN WDM for LR4. So we got there now 20 nanometer spacing. Same frequencies or wavelength used like in 100 gigabit. So starting at 1270, 1290, 1310, and 1330 nanometers. And for the data center interconnect and also that breakout scenario I showed here, where we have 4 times 100 gigabit, this IEEE standard DR4 was introduced. So that's a pure breakout standard, doing 4 times 100 gigabit up to 500 meters with single wavelengths running at 1310 nanometers. That's pretty unique, and I think we will see there some interesting applications coming up. For example, when you look at your exchange points, currently the majority of exchange points only offer LR4, and I'm pretty sure for 400 gigabit there might be the option also that they're going to offer FR4, because the 2 kilometers, they're quite sufficient in the most data centers. And why is it so important? Well, this technology running at 20 nanometer spacing is way cheaper to produce than 5 nanometer spacing, so the transceivers are basically cheaper, and the 400 gigabit links will be cheaper than there as well. And 10 kilometers is not always needed running LR4. Right. LR8 and FR8 are mentioned here just to complete that picture. This is the first generation for the 400 gigabit ones, but the main focus is looking on the second generation, on the LR4, so 4 times 100 gigabit instead of 8 times 50 gigabit. Coming to the plugs, and that's my favorite topic because I really like the latest plugs which were introduced since 40 gigabit with the MPO. In practical fit, I really don't like that plug because it's really a hassle to get along with it in the field. We have 12 or 8 fibers in one single plug, and they have to be aligned quite properly, and you have to clean it, and it's quite a hassle. This MPO is still around. It will be used also for 400 gigabit, but hooray, there will be a new one. It's called the MPO 16, so we got even more density in one single plug. So to enable, for example, multimode technology like SR8, so we have 8 transmitters and 8 receivers. We need in total 16 fibers. They have to be combined in one single plug, and that's going to be the MPO 16. The great thing is it will have a new keying, so you can't mix it up, so you can't plug in an MPO 16 into an MPO 12 receptacle. It won't fit at all because of the keying. Well, for sure, dual LC is still around for single mode, definitely. That's great. These are the good news. And there will be introduced a new one called the CS one. It's called, I would call it the LC double density, basically, because it's an LC just cut in half of the size. Why is this important? Because 400 gigabit itself, as I introduced at the beginning with that breakout mode, you can do 4 times 100 gigabit, or you can even do 2 times 200 gigabit, or 1 time 400 gigabit. But for that 2 times 200 gigabit you want to do there, you need 2 receptacles, and when you look at the surface of a transceiver, you don't, a single LC duplex is enough. You can't place 2 of them, so you need half the size of it, and that's where CS was introduced. So you have 2 times 200 gigabit doable on single mode one. Finally, power consumption, that's a point where I want to stay, is both form factors, and that's a really important question because people are asking here which form factor will make that race in the future. Is it going to be QSFP-DD or OSFP? At the current stage, we see that OSFP has a tiny advantage in terms of power consumption. So we get in there 15 watts of electrical power, and even more critical, we are able to get out 15 watts of thermal dissipation out of that transceiver. And for the QSFP-DD, it's slightly a little bit less. It's 12 watts currently. But the goal is to make them equal, getting up to 15 watts, and I have seen some lab environments where they even try to get up to 20 watts. Why is this power consumption so important? First of all, yes, we want to save power, but for technology which you want to build into those transceivers, you have to drive the optical engines you need when you want to do PAM4 modulation. You need to drive a chip, an ASIC, who is able to do that. He needs power as well. So the more power you can get in there, the better it is. But for sure, you have to get rid of that power as well. And just to give you a rough figure is, if you have 15 watts of power dissipation or heat dissipation of one single transceiver, and the first 1U switches which will be around there, they will have around 36 ports, 1U, with 400 gigabit. So this gives you roughly around 500 watts just of thermal heat dissipation on the optical part. And not taking in consideration that there is a power supply, we got memory, we got RAM, CPU. So you might end up with a 1U switch taking up to 1 kilowatt of power. And you have to get rid of that heat as well. And I think that's an important thing to know. And why, when you compare now a QSFP-28 for 100 gigabit, how they were rated up to 5, 6, 7 watts, and now for the 400 gigabit ones we go to 15 or even to 20 watts. Why is this so important? We want to build in there latest technology and also exceeding those 10 kilometers landmark. So, or 25 kilometers for ER4 distance. The goal is for 400 gigabit is getting in their DWDM technology, getting into a transceiver, coherent DWDM, running up to 80 kilometers. And to do that, you need a DSP, a signal processor, who is able to do the signal, the coherent signal, and this one needs power as well. And this is one big target for the 400 gigabit, not only taking in consideration the small data center or the short distance data center interconnects for 500 meters or up to 10 kilometers. Now also in a later step, I would call it generation 3, going up to 80 kilometers doing coherent DWDM there. From the form factor point of view, the OSFP will be one of the first one which we're gonna see beginning of next year. I'm pretty sure Arista will be one of the first switch vendors who's gonna bring them out on the market. And they are basically the only ones who are running on the OSFP, and all the other major vendors, they jump on the QSFP-DD. I haven't seen any roadmaps yet from the other vendors, but that's the only thing what I know from Arista, that they're gonna do the OSFP beginning next year and gonna be available there. Yeah, that's it. Yeah, that gives still us a lot of freedom to do the programming on the transceivers itself. We have done that for the 100 gigabit, for example, because still the good thing also for us, there is still a microcontroller inside of those transceivers, so we still have to tweak that microcontroller. We have done that for QSFP-28s already, for example, getting ER4s, do ER4 transceivers able to run 30 or 40 kilometers, getting it up and running in a legacy gear or in a gear which is intended to only support up to 10 kilometers. So that's basically how we did it, change the configuration of that microcontroller. And that brings me to the end of the presentation. Thank you very much, and if you have questions, I'm happy to take them.